Suppose f and g are two functions. Actually, to define composite, some restrictions are to be satisfied by domain range of f and g. But at the outset, we may roughly give the definition like two functions have the composite f, for two functions the composite f, the notation used is this f small circle g, f composite g. Do not omit this small circle. If this circle is omitted, it will mean the product f into g, which is defined by f of x into g of x. It is different. This is defined by f composite g of x equal to f of g of x. So, requirement to have this meaningful will be g of x must be defined, and for that g of x, f also must be applicable. Suppose f is a function from a to b, g is a function from c to d. Your g will be defined only if x belongs to c. Therefore, this function will be definable only for certain elements belonging to C, but not for any element outside C. Even if an element belongs to C, there is no guarantee that f of g of x will be meaningful, because we have more restrictions. F must be defined for g of x. So, requirement 1, x must be an element of C. When x is an element of C, g will be defined. It will have a value in D. For that, f must be applicable. That number must belong to A. Therefore, D must be a subset of A. Then f will be applicable for G. The composite will be meaningful. Normally, definition is given like this. Suppose f a to b is a function, g b to c is another function. Then, whenever f is defined, the image will be in B. For that image, g will be defined. So, g will be applicable. I will have a meaning for which function? Not f composite g, g composite f. F is defined for elements of A. It will shift the elements from A to B. For those elements, g will be applicable. The elements will be shifted to C. This composite will have A as domain and C as codomain. Okay. To have G composite F meaningful, the codomain of B, codomain of F must be same as the domain of G. To have F composite G meaningful, you must have F composite G is F of G of x. To have this meaningful, G of x must belong to the domain of F. Agree? F must be meaningful for G of x. G of x must belong to the domain of F, and F of G of x will be in the codomain of F. Okay. But let us omit these details. Let us simply give the definition like this, and when we are asked to determine the domain of F composite G, we will simply find out for which values G is meaningful. Among those values, for which values F of G of x also can be obtained. Suppose f of x is x square. What is the domain? All real numbers. Range from 0 to infinity. Negative values cannot be attained by f of x. Suppose g of x is root x. Domain will be 0 to infinity, including 0. Range same, 0 to infinity. Can I think of f composite g now? According to definition, this is f of g of x. When is g of x meaningful? When x is a non-negative real number. For that, another non-negative real number is obtained as image. For that non-negative real number, can f be applied? Yes. What will you get? The square of what you have obtained here. What did you obtain here? Root x. What is the square of that? We will be going back to x. Provided x is greater than or equal to 0. When you apply f, it becomes x square. Even though this is meaningful for every x, we cannot omit this condition now. Already we have, once we have imposed this condition, it will continue to remain till end. If more restrictions are to be imposed, we will be going on strengthening the condition, but omission of the condition we can never make. This means for f composite G, even though the formula is simple x square, domain will not be R, will not be from minus infinity to infinity, it will be from 0 to infinity. For this simple function, domain is R, but as a composite of two functions, domain is from 0 to infinity. What is the range? Sorry. What is the range? There will be no change in my earlier statements, domain will remain the same. What is the range? If you do not look at these things, simply look at this, you find that the range is minus infinity to infinity, but in this case that will not be the answer, because yes, by obtaining root x, only after that you have reached this. Without this you can't reach this, therefore range also will be from 0 to infinity. Suppose f of x is 2x plus 3, g of x is 3 minus 2x. What is domain for f? Entire real number system. Domain for G, set of all real numbers. Range for f, set of all real numbers. Graph is a straight line extending from minus infinity to infinity. For G, range is minus infinity to infinity. Let me think of this. F of G of x. And this is this defined for every x? Yes, no problem. No need to impose any condition. What is f of this? I need apply this formula now. With x replaced by this number. 2 into 3 minus 2x plus 3. What will it be? 6 plus 3, 9 minus 4x. To apply this, should we impose any restriction on x? No need. X remains free. The final formula we get will be this. So, is our function defined for every x? Yes. The formula is this. What will be the range? Set of all real x. What is f composite G of 1? 5. What is f composite G of 0? 9. What is f composite G of minus 1? 13. For the same two functions, let me obtain G composite f also. By definition, this is G of f of x. This order is important. When I write f composite G, you will first apply G, then apply f. While computing G composite f, f will be first applied, then G. Okay. G of f of x is 2x plus 3. Should any restriction be imposed? No need, x remains free. G of this 3 minus 2 into 2x plus 3 is 3 minus 6 minus 3 minus 4x. Is x free to take any real value? Yes. Domain, entire set of real numbers. Range, again same thing, R. But you might notice one speciality, f composite G of x is not same as G composite f of x. The operation composition of mappings, composition of functions is not commutative. Unlike addition or multiplication, multiplication are commutative, but subtraction is not. Similar to subtraction, this is a non-commutative operation. Okay. What is G composite f of 1? Minus 7. G composite f of 0? Minus 3. Okay. Let me have one more function together with f and g. Suppose f of x is x plus 1, g of x is say 3 minus 2x, h of x is another linear function. For sake of simplicity, consider a linear function. What I am going to derive will apply for all functions. Say 3x minus 1, let it be. What are the domains of f, g, h? All real numbers. What are the ranges? All real numbers for each of the functions. I want to find now composite of the 3 in 2 different orders. First, I will try to find this. I am checking for associativity. Next, I will obtain the order is maintained, but parentheses are placed in different places. I found operation is not commutative, just want to check whether it is associative at least. This will not give a proof, or this will not give a proof for the statement the operation is associative. It is only a verification. Let us try that first. Suppose we get these two unequal. At this stage itself we may conclude the operation is not associative. By definition, this will be, what should I do? First apply this to x, then to the result I must apply f. F of G composite H of x. Agreeable? Treating this as one single function t, my requirement is f composite t, it is f of t of x. Now, for computing this expression, first I must obtain this. This is f of G of H of x. Am I right? G composite H of x is G of H of x. Okay, I think. Substituting, f of G of H of x is 3x minus 1. No restriction imposed on x. This is f of G of 3x minus 1 is 3 minus 2 into 3x minus 1. How much will it be? 3 minus 2 into 3x minus 1. 1 minus 6x. 3 minus 2 into 3x minus 1. This coefficient is okay. This is right. And when you apply f to this, you have to simply add 1 to the argument. Calculation is simple now. You are getting 6 minus 6x. Next, let me try to obtain this at an arbitrary point. This, according to definition, will be f composite G of H of x. Agreeable? And when you apply definition for H of x, it will give you f composite G of 3x minus 1. Now go for the definition of f composite G. This is f of G of 3x minus 1. Agreed, I think. What is G of 3x? Am I getting the same thing once again? Are we copying the steps everywhere? Huh. Yes. What difference? Here also we got f of G of 3x minus 1, f of G of 3x minus 1. Huh. Yes. Yes. This should be evaluated first. Why should I? I am finding this number, then I am applying f composite G to it. See, this is not your multiplication of real numbers or applying operations of that kind. There I agree. Suppose you are required to find an expression like this, you will have to first evaluate the expression within parenthesis, then add to that this constant c, removal of brackets changes the value. Now this is not that situation. You are required to find the image of a number under this operation. This is composite of a new function capital F with a new function capital G. Definition: capital F of capital G of x. Applied capital G of x. Now I have to apply capital F. But how is capital F applied? First apply G, then apply F. Is it not? The procedure is perfect. Are you going to get the same thing? What does that mean? The operation is, in this particular example we find, it is associative. Not only in this example, even in general, it may be proved that the operation is associative, even though it didn't come out as a commutative operation. It is an associative operation for any three functions with involved composites meaningful. If one of these two is not meaningful, then that is a different situation. If both are meaningful, they will be equal to each other. Operation is composite. Operation is associative. A few numerical examples, just to have a little bit of practice on evaluating composites. Simple examples. What will be expression for F composite G of X? Simple application of definition. F of G of X. F of G of X is root of x plus 1, x minus 1. But now you will have to impose a condition on x. Root x minus 1 is not obtainable at an arbitrary x. What is the requirement now? 1. Apply F now. When you apply F to this, you will get square of this number plus 3, x minus 1 plus 3, x plus 2. Should I impose any more extra condition on x? No need. The previously applied condition remains. So this will be my composite function. What is the image of 1 under this composite? 3. Let me next try for the same two functions G composite F. Again, repetition of applying the definition. We are simply trying to obtain some practice over computations of this kind. This is G of F of x is x square plus 3. Should any restriction be imposed on x? No, it is always defined. Now apply G. G will be root of argument minus 1, root of what is here minus 1, root of x square plus 2. Is this very well defined? Yes. Because x square is a non-negative quantity, plus 2 will be another strictly positive quantity. No problem in finding the square root. The two composites not only differ in their formulae, but also differ in their domains. One more example, numerical example. Suppose f of x is defined by root of, I will use two formulae to define f, x square plus 5 if x is a rational, and 2x square minus 1 if x is an irrational. Does these two statements cover all possible real values? Will the domain now become the set of all reals? Yes. No point has been left outside. Okay. Next, second function G, let it be defined by, again piecewise I am going to define it, root of 1 plus 3x if x is a rational, and 3 minus x square if x is an irrational. So what will be f of root 2? F of root 2, x is irrational. Now you will have to apply this formula. 3 or 7? 3. What is f of 1? Root 6. F of 0? Root 5. F of pi? 2 pi square minus 1. G of 1? 2. G of 0? 1. G of root 3? 0. I want a simple numerical calculation, not general formula. G composite F composite G of root 2. I want to just make the evaluation of this. No need to obtain the general formula for the composite. Is the answer obtained already? G composite F of G of root 2. G of root 2 is 1. This is G of F of 1. F of 1 is root 6. Next, G of root 6. G of irrational root 6. That's all. My next example will be little bit more involved. Again, we will have two functions, x plus 2, x less than or equal to 1, 3x minus 2 or 3x, okay, minus 2, x greater than 1. Let G be defined by, there is nothing special in choosing the coefficients or forms, just one set of formulae required, I used them. Randomly is chosen expressions. X square plus 3, x less than or equal to 1, 5x plus 1, x greater than 1. Just to have a variety, let me change this number. Why should I have the same intervals or breaking point of the domain in both the cases same? Let it be different. Let us have a variety. Our job is to determine a few composites, say F composite G, G composite F, F composite F, G composite G, and one more composite of 3 functions, F, G, F. All these things we will try now. What is first F composite G? According to definition, it is simply f of g of x. But what is g of x? G of x is defined by different formulae for different sets of values of x. It is x square plus 3 for x less than or equal to 2, and it is 5x plus 1 for x greater than 2. Now I have to apply f for these numbers. When x is less than or equal to 2, my x square will be less than or equal to 4, and this will be less than or equal to 7. Our argument of f in the first line is a number less than or equal to 7. What formula will be applied in obtaining f for values of x less than or equal to 7? Both. How can you apply both simultaneously? You have to break the interval. For values of x less than or equal to 1, one formula is applying for x greater than 1 different. So let us determine beforehand when is this expression less than or equal to 1 and when is this expression greater than 1. If this expression is less than or equal to 1, we will apply this, and in the other case this will be applied. When is this less than or equal to 1? Never. This is always greater than or equal to 0. This is always greater than or equal to 3. Never it is less than or equal to 1. It is always greater than 1. It is greater than 1 and remains less than or equal to, as you noticed earlier, 7. For such numbers, the formula to be applied is this.
Less than 2, it can go to x square can go to infinity. Less than 4.
Okay. A mistake has been committed. Our function involved is a quadratic. It is not a monotone function. It decreases from yes, infinity to a certain point. Thereafterwards it goes on decreasing. If I draw the parabola, parabola will be like this. Now I am saying x is less than or equal to 2. When x is less than or equal to 2, if 2 is on this side, I think we will have less problems. If 2 is here, then also there may not be more serious problem. But 2 is on this side, function will not be monotone. It will be partially decreasing, partially increasing. I cannot simply say that just because in this portion it is less, throughout it is less, I can't say. It may take greater values on as you go far away from that point where the function vanishes. Let us deal with the situation more closely. Okay. First requirement, this one. When is the argument less than or equal to 1? We find easily this can never be less than or equal to 1. It is always greater than or equal to 3. Okay. That much is enough for me to decide which formula I need apply in finding f. F is obtained by applying one of these two formulae. This applicable for argument less than or equal to 1, this applicable for argument greater than 1. I have noticed that this is not less than or equal to 1. Not less than or equal to 1 means it must be greater than 1. That is, what is happening is this height itself will be greater than 1. Throughout it will be greater than 1. In that case, what formula is used? This one, and you will be getting 3 into argument minus 2, 3 into this number minus 2, 3x square plus 7. Agreed. That confusion part we could avoid. Next, finding image of 5x plus 1. Now there is no complication. This is a linear function. Graph is a monotone increasing function. Slope is positive, monotone increasing. If x is greater than 2, clearly this will be greater than 11. Okay. Which formula? Again, second formula only. 3 times the argument minus 2. 3 times this number minus 2. 15x minus plus 1. Okay. Over. Definition is complete. Do you find the function defined everywhere? Yes. Domain, entire set of real numbers. What is f composite g of 1? 10. What is f composite g of 2? 19. What is f composite g of 5? Okay. Next experiment, finding g composite f. Simple application of definition gives this much. Now proceed to apply definition of f. G of f of x is x plus 2 if x is less than or equal to 1, and f of x is 3x minus 2 if x is greater than 1. Next is to apply g. Linear function, simple linear function, monotone increasing function. I am taking more care now at every point. Is a monotone increasing function, no problem, no scope for any confusion. X less than or equal to 1 will be less than or equal to 3. Am I right? Less than or equal to 3 means it covers all numbers from minus infinity to 3. What about g? Is it defined by a single formula for all numbers from minus infinity to 3? No. One formula is applied for numbers less than or equal to 2, another formula for higher numbers. Let us mark where this expression will be equal to 2. When is this equal to 2? X equal to 0. When x is less than 0, this will be less than 2. When x is equal to 0, this will be equal to 2. When x is greater than 2 but less than or equal to 1, this will be greater than between 2 and 3. First part x, shall I include equality with that? Can 0 be included? 0 be included in that line itself? Yes. When x is less than or equal to 0, I will have this less than or equal to 2. When argument is less than or equal to 2, this is the formula. Apply it. You get square of this plus 2, plus 3. Square of this plus 3 is 7. Next interval of definition will be 0 less than x. We cannot jump to this point. We have to deal with this interval yet completely. Only a part of this has been taken into consideration so far. Remaining portion is 0 less than x less than or equal to 1. Now, this argument will be a number between 2 and 3. For such numbers, this is the formula: 5 times the argument plus 1. 5 times the argument is 5x plus 10, 5x plus 10 plus 1, 5x plus 11. X greater than 1. Function is enough simple, linear, monotone increasing. So, this will be greater than 1. For numbers greater than 1, do you have a common formula applicable? No. For numbers between 1 and 2, one formula. For numbers greater than 2, another formula. Breaking point is 2. When is this equal to 2? X is equal to 4 by 3. 3x minus 2 equal to 2 means x is equal to 4 by 3. When x equal to 4 by 3, this will be 2. So, split this interval like 1 to 4 by 3 and then 4 by 3 to infinity. Where should I include 4 by 3? In this line or in this line? When x is 4 by 3, this will be equal to 2. Which line will be applicable when number is equal to 2? First line. So, where should I include 4 by 3? X is between 1 and 4 by 3, 3x is between 3 and 4, 3x minus 2 is between 1 and 2. This is the formula: square of the argument plus 3. Square of the argument plus 3. 9x square minus 12x plus 4 plus 3, 7. Last case, x greater than 4 by 3. This is greater than 2, argument greater than 2, 5 times the argument plus 1, 5 times the argument plus 1, 15x minus 10 plus 1. Agreed? What is G composite f of 1? 16. What is G composite f of 0? 7. What is G composite f of root 2? Which line? Last line. 15 root 2 minus 9. What is G composite f of pi? 15 pi minus 9. What is G composite f of minus 1? Okay. For the same two functions, let us obtain few more composites. Next, I will be trying F composite F, then G composite G, then F composite G composite F. For x less than or equal to 1, f of x is x plus 2. For x greater than 1, f of x is 3x minus 2. We have to apply f once again. x is less than or equal to 1, this is less than or equal to 3. For numbers less than or equal to 3, will same formula cover function values? No. Up to 1 you have one formula, from 1 to 3 you have a different formula. Breaking point is 1. When is this expression equal to 1? Minus 1. Agree? This is how we have to break the interval. Minus 1 will be included here. Agreed? I think. X less than or equal to minus 1. This is less than or equal to 1. So, image under f will be argument plus 2, existing value plus 2. X is between minus 1, 1. So, this will be between 1 and 3. Am I right? Excluding 1, 1 and 3. Formula to be applied is this: 3 times the argument minus 2. 3 times what you have here minus 2. Good. Next line. X greater than 1. This is greater than 1. Is same formula usable? Yes. This formula. 3 times the argument minus 2. No need to break the interval further. 3 times this minus 2. 9x minus 8. Procedure clear, I suppose. Let me try G composite G next. Some complication we may come across now because of this higher degree here. Let us experience it. X square plus 3, x less than or equal to 2, and 5x plus 1, x greater than 2. Once again I have to apply G. For what values of x, this will be less than or equal to 2. In order to apply the first line, I need the argument to be less than or equal to 2. For what values of x, this is less than or equal to 2? Never. It is always greater than 3. Okay. Again, our job has become simple. For every x, this is greater than or equal to 3, certainly greater than 2. So, the line to be applicable is this one, 5 times the argument plus 1. 5 times what you have plus 1. Next line, g of 5x plus 1, x greater than 2. When is 5x plus 1 less than or equal to 2? When is 5x plus 1 greater than 2? First, let me identify when is 5x plus 1 equal to 2. 5x plus 1 is equal to 2 when 5x is 1, x is 1 by 5. Is 1 by 5 a point of this interval? No. So, in this interval that breaking point does not lie. Therefore, throughout the interval it will satisfy one of the inequalities throughout. Therefore, only one of the formula will be applicable throughout, no breaking necessary. Identify that formula and apply it. X greater than 2, greater than 11. When greater than 11, it is greater than 2 also. 5 times what you have plus 1. I thought it will be more complicated, but it became more simple. Okay. My next attempt will be to find composite of F with G, again with F. You know, operation composition of mappings is an associative operation. No need to place any brackets inside. So, you may apply first F, then G, then F, or you may first apply G composite F, then F, or you may first apply F, then F composite G. Anyway, you may apply the operations. Have we already obtained any one of the factors of this composite expression? Yes, we have obtained G composite F. We have obtained F composite G. Both have been obtained. You may make use of any one of them now to reduce the work of computation. Let me treat this as, how do you feel like treating this? F of G composite F or F composite G of F? F of. Taking G composite F as one of the functions, treating the required composite as composite of two, capital F, capital G, where this is capital F, this is capital G. I am applying first capital G, then capital F. Okay. This has already been obtained. I will take the advantage of that. Yes, what is G composite F? I have forgotten. First line. X less than or equal to 0. F of 5x 11. One. 9x square 12x 7 less than x 4 by 3. And last line 15x minus 9 4 by 5. Once again, F is to be applied to the various arguments. X is less than or equal to 7. Can something be said about this? Because the function is not monotone, it is partially decreasing, partially increasing. Directly I cannot substitute the value and apply this inequality. We will have to be more careful. Either you consider the graph or apply one algebraic method, the method of completing squares. Suppose you apply completing squares method, x square plus 4x is x plus 2 whole square plus 3. Agreed. This means function value is always greater than or equal to 3. When function value is greater than or equal to 3, is a common formula applicable? Yes, this formula. No need to break the interval further. 3 times the argument minus 2. Interval has not been broken further, it remains as it is. Next, this is a simple function. We have less complications now. X is between 0 and 1, excluding 0. This will be between 11 and 16. 11 and 16, which formula? This one again. 3 times the argument minus 2. 15x 0 less than x less than or equal to 1. Next, quadratic, we will have to be a little more careful. As before, let me apply the method of completing squares first. It is 3x minus 2. How? Okay, 3 into 2, 6 into 2, right, will be 12. 3x minus 2 whole square, 9x square covered, 2 into 3x into 2 minus 12x covered, plus 4 is covered now, plus 3. Again, perfect square plus 3, therefore always greater than or equal to 3. For numbers greater than or equal to 3, common formula, 3 times the argument minus 2. Yes, sir. 90. 1 less than x less than or equal to 4 by 3. Last line. X greater than 4 by 3. 15x will be greater than, linear simple substitution. 15x greater than 20 minus 9, 11. Argument is greater than 11. common formula 3x minus 2. Now we didn't make use of this anywhere. Okay, 3 times the argument minus 2. 45x minus is our composite function. Is the procedure clear? Fine. What is f composite g composite f of 0? This is the composite. Value at 0, 19. Value at root 2, 45 root 2 minus 29. Okay. Shall we have one more example, a function in which we will be using 3 formulae to define the function. Method same as before, more computations, that's all. X is less than 1, x plus 1 is less than 2. Less than 2 means it may be greater than or equal to 1, less than 2, maybe even less than 1. So, there will be a need to break the interval further. Find where is this equal to 1? 0. We will break the interval at 0. Where should 0 be included? First line or second line? Second line. For x strictly less than 0, this is strictly less than 1. When number is strictly less than 1, this is the formula. Image will be the argument, existing argument plus 1. Agreed? Next, x is between 0 and 1, including 0. This will be between 1 and 2. Agreed? Including 1. Between 1 and 2. When number is between 1 and 2, this is the formula. 3 minus 2 into existing value. 3 minus 2 into what you have there? Yes, yes, yes. 1 minus 2x. Good. Next line. X is between 1 and 3, including both endpoints. This will be between minus 3 and 1. Is a number between minus 3 and 1. Is same formula usable for all values between minus 3 and 1? Except 1. For every other value, common formula is applicable. The point 1, we will keep it separately. Okay. 1 less than or equal to x. Sorry, 1 is to be kept separately. So, x equal to 1 first. Then 1 less than x less than or equal to 3. Let us have a proper order. When x equal to 1, this is 1, and for x equal to 1, the image is 1. Is it not? This 3 minus 2x is 1. What I am to find is f of 1. What is f of 1 according to this definition? 1 again. No change in the value of the argument. X is next between 1 and 3. This will be between, I forgot the interval, minus 3 and 1. Interval will be this. The formula to be applied is this: existing value plus 1. Am I right? Yes. Last line, x greater than 3. We know this being a perfect square is greater than or equal 0, the sum is greater than or equal to 3. Is a common formula applicable for all x greater than 3? Greater than or equal to 3? No. One formula at 3, the other formula for values greater than 3. First let us record the formula applicable at x equal to. Did we cover 3 here? Okay, that is different. Now this is becoming 3. This is becoming 3 when? X is 0. Is 0 a point of this interval? No. For points of this interval, this will be always greater than 3. Agree? So no need to break. Apply just this last formula, x square plus 3, the formula x square plus 3, you get the definition applicable for x greater than 3 as square of existing value plus 3. Is it fine? Next, some special properties that can be expected of functions. You know, in general, by a function, we just mean any rule which associates with every element of a set A a unique element belonging to B. There will be 2 sets, need not be finite, maybe infinite also. Every element must have an image and must have that image belonging to this set. That image must be uniquely defined. The only restrictions are every element must have an image, no element must be there without an image, every element must have a single image, no element must have multiple images. Okay. This does not impose any condition on these elements. It does not impose the requirement that 2 different elements cannot have same image. 2 different elements may have same image, we permit it. Suppose different elements of this set have different images in this set, is an extra condition. Suppose that is satisfied, we call that function a 1-1 function or an injective map. A function is called an injective map or injective mapping or a 1-1 function if, in addition to being a function, different elements are, this is not always required to have a relation called a function, if different elements have different images. For example, if we have something like this, it will be a 1-1 function. Suppose we have a correspondence like this, it will be a function, but it will not be 1-1. Suppose you consider f of x equal to x, it will be 1-1. Because different x, different images. Suppose you have f of x equal to x square, this is 1-1, this will not be 1-1, because -1 plus 1 have the same image, -2 plus 2 have the same image, -3 plus 3 have same image. Infinitely many pairs of elements are there having the same image. Suppose you have f of x equal to x square plus 1 is not 1-1. Again, -1 and 1 have the same image. -2 plus 2 have the same image. Suppose you have f of x equal to x square plus x plus 1, not 1-1. Why? Now it may be difficult for me to find the numbers having same image, not difficult, making some calculations we can find. Easier method, draw the graph. We find, draw any horizontal intersecting the graph, you get 2 points of intersection. This means what? For this number, the image is this height. For this number also, image is same height. That means these two numbers on the x-axis have the same image. Among the various points on the x-axis, this point has a single image. Every other point has multiple images, 2 images each. Do you find it? Yes. Suppose instead of taking the whole interval as domain, I restrict my domain only to this part of the real line. Then the function becomes 1, 1. Suppose I consider only this part of the real number system as the domain, function becomes 1, 1. Suppose I include these points, it will not be 1, 1, because one small portion will be intersected by a horizontal at 2 points. Do you notice it? Yes. Now not 1, 1. As long as your domain contains points on both sides of the vertex, it will not be 1, 1. If the domain contains points belonging to only one side of the vertex, the function will be 1, 1. Even though it is quadratic, it will be 1, 1. What about the x cube? 1, 1. By drawing the graph, you can see it is monotone increasing. From minus infinity to infinity, it goes on increasing. Not 1, 1. No trigonometric function defined as a function from R to any set is not 1, 1. Agree? If you retain the entire set of reals as the domain, not for the reciprocal function, sine cos, only 2 functions, sine cos. For others, domain will not be the set of real numbers. Only for these 2 functions, if you retain the set of all real numbers, you will not find the function to be 1, 1. Even for tan x, secant x, other functions, you consider the set of all points where the function is meaningful. Take that as the domain. Graph will be intersectable by by a horizontal at more than one point. It will not be a 1, 1 function. Okay. Suppose for this, I consider only this portion of the real number system as the domain. Will the function be 1, 1 at least now? No, this covers all the 4 quadrants. So the function will not be 1, 1. Repetition takes place. Repetition of values attained by function in the first quadrant will again take place in the second quadrant. Third quadrant values are again repeated in the fourth quadrant. Will the function be at least 1, 1 now? No, not even now. First and second quadrants are there where values repeat. Yes, now it is 1, 1. Fourth and first quadrant. Are values repeated? Fourth and first quadrant. One is a negative quadrant, one is a positive quadrant. Values are not repeated, will be 1, 1. This is one of the largest intervals on which this function is 1, 1. Defined as a function from R to R, not 1, 1. Because graph will be something like this. When you draw a horizontal, it will be intersecting the graph at more than one point. The geometric way of describing 1, 1ness is, you consider the graph, draw any horizontal. The horizontal either must not intersect the graph, or if it intersects, it must intersect at only one point. Then the function will be 1, 1. If the graph is not intersected by a horizontal at more than one point, then function is 1, 1. If the graph is intersected by some horizontal at more than one point, it is not 1, 1. Okay. This is not 1, 1 as a function from R to R. No, not 1, 1. All 4 quadrants are included. Yes, one negative quadrant, one positive quadrant. Every positive, only one positive quadrant included, only one negative quadrant included. It is 1, 1. No, not 1, 1. A negative quadrant is taken twice, second and third. Am I right? Yes. Not 1, 1. Positive quadrant is repeatedly made use of. So, one of the largest intervals on which this is 1, 1 is 0 to pi. We will use these ideas once again later in trigonometry while defining inverse trigonometric functions. Okay. Not 1, 1 clearly treated as a function from not r to r, but r minus odd multiples of pi by 2 to r, treated as a function between those sets, not 1, 1. Okay, let me shorten the length of the interval. Not 1, 1. All 4 quadrants included. Not 1, 1. Quadrants included are 1. What about 1, 1? Is it 1, 1? Yes, one positive quadrant, one negative quadrant is 1, 1. Right. Is 1, 1. One positive quadrant, one negative quadrant. What is tan pi? What is tan pi? 0. What is tan 2 pi? Is it 1, 1? Here also, what is tan 0? What is tan pi? Are not they equal? Is not 1, 1. For the reason there is one point where function values are equal. Just for the presence of those end points, it is not 1, 1. Now it will be 1, 1. Now it will be 1, 1. You cannot include both the end points. You retain only one of the end points. Now it will be 1, 1. Okay, I think. No, even now we are wrong. There is a point where function is undefined. There is a point where function is undefined. So this cannot be accepted as domain of the function, not domain. I can only write this is an acceptable set, a set acceptable as domain. Over this set, function is 1, 1. Similarly, with some modification, we can make this 1, 1, removing pi by 2. Okay. Standard way of choosing is minus pi by 2 to pi by 2, leaving both the endpoints. Now there is no need to give any importance to the endpoints. So both endpoints are left out. They are the points where function is undefined. You do not get multiple points having same image. Function remains 1, 1. On this set, you will be later defining inverse for tan. Not 1, 1 as a function from R to R. Clear? When treated as a function from Z to Z, is 1, 1. Is 1, 1. Agreeable? For every integer, itself is the integer part. There will be no pairs of integers having same integer part. As it is, as a function from R to R, not 1, 1. But if I restrict my domain to, okay, let me have a specific value for n. Will the function be 1, 1? No. Either remove 1 or remove 0, any one of that. Then the function becomes 1, 1. Okay. Consider this as a function on this set. I am considering only this part, short interval, as a domain. A function is defined at every point of the domain, can be chosen. Will the function be 1, 1 now? Yes. will now also be our function, sorry, will now also be our function 1 1 half to 4 by 3. This is our graph. We are starting from here and ending somewhere here. Of the 2 points, this is included, this is excluded. Will the graph be 1 1? Only this portion retained. That means this portion retained. Will the graph be 1? Will the function be 1 1? Draw any horizontal. Is there any possibility of getting more than one intersection? No. Like this, to what stage I can go up to on this side? 3 by 2. Even now, this is one of the largest intervals. The function will be 1. I can even include one of the endpoints, not both, either half or 3 by 2. One of them can be included, still function remains 1 1. But for any increase in the size of the interval, that property will be lost. Okay. Is this function 1 1? Yes. For different numbers, you get different logarithms. There are no two numbers having the same logarithm. Domain may be different, it is not R to R, it is from 0 infinity to R, no problem. When defined, do there exist numbers, different numbers having same image? No, is 1 1. Is 1 1. Imagine the graph if you want. It is a monotone increasing graph. Draw any horizontal. Graph is intersected at a single point. Is 1 1. Is 1 1. Is 1 1. Okay. Not 1 1. Suppose I restrict my domain to 0 1. Domain is restricted, not interval, set of 2 points, 0 1. My domain is containing only 2 points. Will be 1 1. What is signum 0 0? What is signum 1 1? Are not they different? No, I am not considering interval. I am considering set of 2 points. Brackets, use the flower brackets. I am considering a set with just 2 points, 2 element set. Not 1 1. These 2 elements will have the same image. 1 1. One one. Let me draw the graph. I am considering this with domain. Will the function be 1 1? Yes. Did I go to the right of minus half? Yes. Did I stop before reaching minus half? Yes. Did I start at a point to the right of minus half? Yes. Hope you are following. Just to look at the graph, you get the conclusion. No, we have points on both sides, either sides of minus half. Okay. Suppose your formula is a little bit more complicated. So far as examples, I was considering very simple functions. Suppose you have a formula like say x square plus x plus 1 into 2x minus 1, something like this. How do you check whether the function is 1, 1? Very simple, efficient method. Definition says, as long as x1 is not equal to x2, you must have f of x1 not equal to f of x2. This is our requirement. Different elements must have different images. Apply negation on both sides. You will find this is exactly same as claiming if f of x1 is equal to f of x2, if two image elements are equal, then their pre-images must be equal. If this implies x1 equal to x2, whenever f of x1, f of x2 are defined, equality implies equality here. That means function is 1, 1. If this implies this and together with something else, this you will always get. Together with this, if you get something else also, that means function is not 1, 1. For example, you consider x square. x1 square equal to x2 square means x1 equal to plus or minus x2. Function is not 1, 1. Consider 2x plus 1. 2x1 plus 1 equal to 2x2 plus 1 implies x1 equal to x2. Function is 1, 1. Hope it is clear. Suppose you consider x cube. x1 cube equal to x2 cube means x1 equal to x2. Function is 1, 1. Suppose you consider x to the power 4 plus 1. x1 power 4 plus 1 equal to x2 power 4 plus 1 means x1 power 4 equal to x2 power 4 means x1 equal to plus or minus x2, does not mean function is 1, 1. Means function is not 1, 1. Is the procedure clear? Sin x1 equal to sin x2 means sin x1 minus sin x2 0 means 2 cos x1 plus x2 by 2 into sin x1 minus x2 by 2 equal to 0. This means either this equal to 0 or this equal to 0. Even if you consider this component, this equal to 0 means this argument may be 0, maybe pi, maybe 2 pi, infinitely many possibilities. So x1 and x2 may be equal, x1 minus x2 may be equal to 2 pi, x1 minus x2 may be equal to 4 pi, so many possibilities. Function not 1, 1. Is it clear? Examples a little late. Some problems you have to work out on 1, 1 functions little later. Before that, let me give definition for onto function. In general, when f is a function from a to b, f is a function having a as domain, b as codomain, you need not get range equal to codomain. You must have seen in examples. For example, sin may be defined as a function from R to R. Domain will be this whole set, but range is not the whole set, it is only the interval -1 to 1. By chance, if you get range equal to codomain, we say the function is onto. A function is said to be onto if the range is codomain. In other words, if every element of the codomain is an image element, if every element of the second set is a relative of some element belonging to the first set. For example, this is not onto. Here is an element which is not image of any element. It is a function. Every element here has an image, has a unique image, is a function, is 1 1 also. Distinct elements are having distinct images, but in this set you find an element having no pre-image. This is a case of a not onto function. Function is 1 1 but not onto. Suppose I define it like this, now it becomes 1 1 as well as onto, we call it a bijection. 1 1 function is also called a injection, not injection, injective map. Okay. Onto function is also called a surjection or surjective map. A function which is both 1 1 and onto is called a bijection. Both 1 1 onto and bijection mean one and the same. So, this will be an example of a bijection. This will be an example of a function which is onto but not 1 1. Surjection which is not an injection. Okay, I think. Suppose you have one element here, it is neither 1 1 nor onto. Suppose you have one more correspondence like this, not a function. Good. Treated as a function from R to R. Is it onto 1 1? It is. We have examined that. Is it onto also? Yes. You know the graph of 2x plus 1. A line with slope equal to 2. A line starting at minus infinity going up to plus infinity, covering every real value. Therefore, it is an onto function. It is a bijection. It is 1 1 onto both, therefore a bijection. Treated as a function from R to R. It's not 1 1, we have noticed it. Is it at least onto? No. There are so many elements here not having any pre-images. Minus 1 has no pre-image. No negative number has a pre-image. Only non-negative numbers have pre-images. As a function from R to R, it is neither 1 1 nor onto. But if it is treated as a function from R to 0 infinity, it will be a onto function, a function which is not 1 1 but onto. Agree? Not 1 1, f of minus 1, f of 1 are equal, but onto every element here is an image element. Can I further shorten this interval? This ceases to be a function now. There is no image for 0 belonging to this set now. Is it clear? I cannot further shorten the interval. I can increase the size of the interval, losing the property of ontoness, but I cannot reduce it from the previous stage. Okay, now it is not 1 1 but onto. Not 1 1 but onto. Okay. What is the graph? Graph is something like this, with this as 0 0. I am considering minus 10 to infinity, not 1 1 but onto. Clear, I think? Yes. Only from here onwards, 1 1 as well as onto, bijection. One but not onto. Numbers between 0 and 1 do not have pre-images. Hope you are following. Okay. Not 1 1 but onto. Okay. Is it a function? Yes. What about ontoness? 1-1ness? Yes, it is 1-1. Different numbers have different logarithms. What about ontoness? Can any number, real number, be obtained as logarithm of a number? Can 0 be obtained as log of a number? Yes, log of 1. Can a positive number be obtained as log of a number? Yes. Negative numbers? All numbers are obtainable. If you want, you can imagine even the graph. Graph extends from minus infinity to plus infinity. Do you remember it? You can recollect. You have a copy with you. You can refer to it. It is onto as well as 1-1, a bijection. Now also it is a function. What kind of function? Still, is the function still 1-1? Yes, 1-1ness is not lost. Always 1-1ness affected when you change this. No. When you change this, is 1-1ness is affected by changing the domain. If I increase the size of the domain, sometimes it happened here. The function fails to remain 1-1. Okay. Even codomain, that also has an effect on the property of 1-1ness. By changing the codomain, a function can be made 1-1. We can make it fail to be 1-1. Both possibilities. Let me consider that later. Now this is my domain. Is the relation a function? Yes. Is the function still 1-1? Yes. Is the function onto? No. For numbers between 0 and 1, certain numbers are obtainable as logarithms. They were there here. Those elements now will not be having pre-images. Function fails to be 1-1 now. What about this? Is the relation a function even now? For numbers greater than 1, is logarithm greater than 0? My base is 10. It also depends on the size of the base. If the base is less than 1, something else happens. If the base is greater than 1, another property will happen. Now the base is greater than 1. For numbers greater than 1, are logarithms greater than 0? Yes. This is the common logarithm. Base 10 means the logarithm you obtain by referring to the logarithmic tables. That same logarithm I am referring. For numbers greater than 1, logarithms are greater than 0. So this is a function, no problem. Is the function 1-1? Still different numbers will they have different logarithms? Yes. Is the function onto also? Why not? Don't you get an anti-logarithm for every number here? Won't you get that anti-logarithm as a number greater than 1? Can't you find anti-logarithm for numbers greater than 0? For every number, positive number, can't you obtain an anti-logarithm? You can actually find anti-logarithms for all numbers. And when you apply anti-logarithm for positive numbers, won't you get the anti-logarithm as a number greater than 1? For a number less than 1, can you have logarithm greater than 0? It is both 1-1 onto, it is a bijection. Now it is a function 1-1, but not a onto function, fails to be a bijection because the element 0 of the other set has no preimage. Okay. Now relation remains a function, remains 1-1, remains onto, is a bijection. Image of 1 is 0. Not a function at all. For numbers greater than 1, logarithm to the base half will be less than 0. Graph shape is different now. Okay. What is f of 2? 1. What is f of 1? 0. What is f of 10? 5. What is f of 5? 0. What is f of pi? Not defined. My function is defined on only on z, only for integral values. Okay. Is the function 1 1? No, clearly not 1. Every odd number is having image equal to 0. F of 1 is 0, f of 3 is 0, f of minus 7 is 0. Okay. Is the function at least onto? For 0, do you have a pre-image? Yes. So many pre-images are there, infinitely many. For 1, do you have a pre-image? Yes, 2 is a pre-image. For 2, do you have a pre-image? Yes, 4 is a pre-image. For minus 1, do you have a pre-image? Yes, minus 2 is a pre-image. Can you find a pre-image for every element? Yes. Take any integer, whether 0 or not 0, multiply it by 2, it will be a pre-image for that number, because for every even number image is given as x by 2. Agreed? The function is onto, but not 1 1. Can I make it 1 1? By slightly changing the either one of the two, either domain or codomain. How to make it 1 1? Change the domain. By changing the domain, how to make it 1 1? A domain or codomain, whichever you find convenient. Is it possible to make it 1 1? Because you are getting multiple images for, you are getting common image for all odd numbers, the function fails to be 1 1. Now, among these different numbers having image 0, you have to retain one element and reject all the remaining. You retain any one of the numbers having image 0, reject the remaining, then the function becomes 1 1. Let this consist of only even integers. All odd integers have been removed. Do you get image 0 even now? Yes, for the even integer 0, image is 0. Do you get every integer belonging to this set as image of some element belonging to this set? Yes. Now the function is what? Bijection. Both 1 1 and onto is a bijection. Okay. One point may be remembered among two functions f and g. Suppose g is a bijection, then for any f, f composite g also will be a bijection. Just usable. I think you will be given some notes. Yes, you will have that point mentioned. No need to copy anything. Some examples. F R to R is defined by this. You have to examine for 1 1ness, onto-ness, determine whether function is a bijection or not. We will be doing that. This also is defined from R to R. Oh, some of these have already been described. Doesn't matter. Let me note down. I am sorry, I was copying it differently. All these have been covered already. Sorry, I don't have anything remaining. Everything has been covered in some form or the other. With minor changes, I have covered everything. Okay, let me just for having started writing something, let me include one example. Examine whether the function is 1 1 or not, or onto or not, bijection or not. Simple one. Yes, not 1 1. Reason? Mention two elements having same image, some two elements. -3 and -3. Image is -2 and -1. Minus +4. +4 image also is -2. For that, one reason is enough. Function is not 1 1. What about ontoness? Is it onto? You try on your own. Okay. Is this job finished? What is the conclusion? Onto. It is onto, but not 1 1. So not a bijection. Fine. Domain not mentioned means you take the entire set on which the formula makes sense as the domain. Okay. You are required to examine for ontoness also. Codomain not given. You accept whole real number set R as the codomain. You have to examine taking the function taking f as a function from R to R. You have to examine for 1 1ness and ontoness. In this case, only 1 1ness, except the entire set on which this formula makes sense as the domain. I do not know whether it is the entire set of real numbers. You will have to find out how to examine for 1 1ness. Trial and error, very simple. No method need be applied. There are two factors, two quadratic factors. Do you find something common in the expressions occurring as factors here? Yes, x square minus x is common. Is it a quadratic having two different real roots? Yes. What are the roots? 0 and 1. At 0 and, I think I am right, 0 and 1. For x square minus x, what are the roots? 0 and 1. That means both at 0 and 1, this expression, only the portion x square minus x takes the same value. Therefore, the whole product also will have common value at both x equal to 0 and x equal to 1. There may be more points also, but to claim that the function is not 1 1, one set is enough for me. I have identified two numbers having same image, function fails to be 1 1. What about ontoness? Does the function cover all values? from minus infinity to infinity. Let me apply the completing squares method. X square minus x is x minus half whole square minus 5 by 4. Yes, 5 by 4. The other factor is x minus half whole square minus. This is not serving my purpose because I will be getting a different number here. No, I will change by track. No, this is not suitable for me. You consider this minus 1 and plus 5. What is average of these two? For minus 1 and 5, what is the average? 2. I will write this as x square minus x plus 2 is the average, no? Yes, plus 2 minus 3. No objection, I think. Second one will be written as x square minus x plus 2 plus 3. Immediately we find the product as x square minus x plus 2 whole square minus 9. What does this mean? This is always greater than or equal to 0, being a perfect square. Therefore, the difference is always greater than or equal to minus 9. No value less than minus 9 is attainable by my function. My function cannot be onto. Clear? Okay, I think. Yes. Neither 1 1 nor onto. Next example. To examine whether x square plus 2x plus 4 by x square plus x plus 2 is 1 1 or not. Only 1 1 is. It is different from the previous example in the sense these two, the portion consisting of these two terms is not common. Had we given x square plus x plus 4 in numerator, x square plus x plus 4 in 2 in denominator, we could have applied the same idea. We could have found two different points having same image, claimed that the function is not 1 1. Now these two coefficients are different. That method fails. How to check whether function is 1 1 or not? By let y equal to cross multiply. Then no, your question is to examine for 1 1ness. By cross multiplying, how do you proceed? That will help you in finding the range. We followed that method in determining the range, claiming that x is real, claiming that the roots of the equation will be real numbers, discriminant must be greater than or equal to 0. We succeeded in finding the range of the function. Now 1 1ness, does it work now also? My idea is different. What I do is, I consider, let me call the function f of x. I consider, start with the equation f of x1 equal to f of x2. Try to find out what does this imply. If I get finally x1 equal to x2, only x1 equal to x2, conclude function is 1 1. If I get x1 equal to x2 or something else also is possible, conclusion function will not be 1 1. Okay. But as it is, if you consider the equation f of x equal to f of x2, you may come across a slightly complicated equation with more terms. What I do is, first try some simplification on this, then go to this method. Slightly reduces my calculation part. What simplification you can perform? I will write this as 1 plus x plus 2 by x square plus x plus 2. This is x square plus x plus 2 plus x plus 2. X square plus x plus 2 divided by this is 1. Next, I need consider only that. Okay. While checking for f of whether f of x1 equal to f of x2 implies x1 equal to x2 or not, I need consider now only this portion. Compared to the original form of the equation formula, this is much simple. We have only linear in the numerator. Okay. So, I will start with my equation x1 plus x2 by x1 square plus x1 plus 2 equal to x2 plus 2 by x2 square plus x2 plus 2. I need find whether this implies only x1 equal to x2 or x1 equal to x2 or something else. Cross multiply x1 x2 square. Here I am getting x1 square x2. I will club the two terms, write x1 x2 into x2 minus x1, bringing all the terms to this side. x1 x2 square minus x2 x1 square. Then x1 into x2, x1 into x2 cancel. x1 into 2, x2 into 2 is 2 into x1 minus x2. x1 part is finished, I think. Now 2 x2 square minus 2 x1 square. Then 2 x2 minus 2 x1. If I go wrong anywhere, please correct me. 2 into 2, 4 minus 4, cancel. This is the equation I am getting. Clearly, x1 minus x2 is common. That corresponds to the possibility x1 equal to x2. I will get rid of that. I need concentrate only on the remaining portion. I need find whether the remaining portion is sensible, whether the remaining portion has values satisfying. If it has values, I should conclude function is not 1, 1. Cancel, remove the factor x1 minus x2. Agreed? What I am left with is what? Huh. Yes. Huh? Heady. 2 into x1 plus x2 plus x1 x2 equal to 0. Am I right? Yes. Question: do there exist real numbers satisfying this equation? Can you find x1 and x2 such that this is equal to 0? Yes. One set. 1. No. Can you guess one set of numbers x1 and x2? 2 and minus 1. 2 minus 1 is 1. 2 into 1, 2. 2 into minus 1, minus 2. The sum becomes 0. This is one set of distinct numbers having same image. If you want, you can have cross checking. At 2, what is the function value? 4 plus 4 plus 4, 12 by 4 plus 2, 6 plus 2, 8. 12 by 8, 3 by 2. The other point, minus 1. 1 plus 4, 5 minus 2, 3. 1 plus 2, 3 minus 1, 2. Are you getting the same number? We have successfully proved or able to exhibit two different numbers having same image. Conclude that function is not 1, 1.